Hello again. This is Roger Kochbar. I'm here for the bioelectricity course to talk to you as a part of week 7 of the course. We're in lecture segment number 7. And here I want to rehash all the same things that we said in the previous segment from a slightly different point of view. What we're trying to figure out is where do these extracellular waveforms come from in terms of events underlying the waveform in the action potential and in the fiber. So here's a drawing of everything laid out in space, once again, sort of elongated on the slide to make it a little bit easier to relate one thing to another. If I now look at the electrode here on the right, then when the action potential at that point is about halfway through its upstroke, the distribution of potential that I see up and down the strand, all the way from one end to the other, that's this voltage, all the way from one end to the other, a spatial distribution. And here on the bottom panel, what I see as membrane current, all the way from one end to the other, is this pattern that's shown below. Let's look at some of the details here and see what we can make out. Now I'll show you a trick that's been used for a long time. In the original history of electrocardiology, people did not have computers for waveform interpretation. They interpreted waveforms mostly by hand. And when they did that, they developed some neat tricks that facilitated manual interpretation. These neat tricks we no longer need insofar as just processing the signals, because it can be done better with computer processing. But the neat tricks are still useful because there's an understanding associated with them, and we'd like to know what that understanding is. So one of the neat tricks that they did was to take their action potentials and convert them into a series of straight lines. So on the screen here, I can't do it very carefully, but you'll see the idea. Suppose we take the slope of the upstroke and we draw a straight line through it. Suppose we take the slope of the recovery and we draw a straight line through it. Suppose we take the baseline, we draw a straight line through it. And similarly for the baseline on the other side. Now our action potential is represented here by 4 straight line segments. The interesting part of this comes from the following. We know that our sources and sinks go according to the second spatial derivative of the transmembrane potential. If we look at the drawing as we have it, the flat lines, the straight line segments, all have a constant slope. That means they all have a constant first derivative. If we want to know where is the place on this waveform where the second derivative has a non-zero value, we'd say, well, it's where these segments join one to the other. So right here, there's a big value of the second derivative, right at that junction. And in particular, the second derivative is very much positive because there's an abrupt change from a slope that's highly negative, this slope is highly negative, to a slope that's 0. Therefore, the slope gets much more positive. The slope changes abruptly from one that's highly negative to one that's much more positive. Therefore, the second derivative is positive. Now, of course, a positive second derivative should result in a source. That's the sign of a current source, current coming out of the fiber. Current has to come out of the fiber there because it is flowing along the fiber here, down this voltage gradient, but no current is flowing over here. So at the junction point within the circle, a lot of current has to come out of the fiber. Sure enough, when we look at the computer drawing underneath, we see right here, there's a source. A lot of current is coming out of the fiber at that point. Now let's do another one. Suppose we take this junction right here. That junction represents a change in slope from a rather sharply upward slope to a rather sharply downward slope. Therefore, the second derivative, which is the change in the slope, the second derivative is sharply negative at that point. Because it is sharply negative at that point, it says current has to come in the fiber at a very substantial amount of current has to come in the fiber at that point in order to accommodate these changes in the axial current flow. So we see, when we look down here on the membrane current trace, that we're at a minimum. And that's exactly what we'd expect from the change in slope. We can do that again. I won't do it right now, but we could do that again over here at our third change in slope. And if we did it over here at our third change in slope, we'd find still another source or sink, depending on how the slope's changed. I think here we'll find a source because the waveform will change from zero slope to positive slope. This kind of manual analysis is extremely useful as far as working with the records manually. Well, nowadays that's not so important as we said, but it's also extremely useful as far as understanding the records that one has. There's a very close correspondence between the straight line version of the transmembrane potential as a function of distance and the transmembrane current waveform. Of course, now, if we put this in terms of an equation, we'd say, well, what we can do is we can write an equation from before, from our previous knowledge. We can write an equation that says Im is equal to some constants here. Do you remember what those are? D squared Vm dx squared. We can get d squared Vm dx squared from the change in slope and the manual procedure that we've just done. And when we do that, we can identify the points along the fiber in terms of whether they're sources and sinks. In this particular case, going back to the fiber diagram, we're going to find there's a source right about there and a sink right about there. So out of this whole fiber at this moment, as far as the extracellular potentials are concerned, nothing matters much except for the source here and the sink there. And this source-sink pair, which is often called a dipole, will over time move down the fiber, and the events that we see as a function of time are caused by this source-sink pair moving from one place to another. So I'll conclude this segment by showing you this interesting carving, the only one I know that we have, that shows someone hidden behind a sports mask. Fascinating. Thank you for watching. We'll see you in the next segment.